There is absolutely nothing that says that when we are collecting data from a subject, we can't collect more than one kind of data at a time. In many cases, when we do collect data on two quantitative variables, call it bivariate data, we can then compare those two data points and see if any kind of trend or pattern emerges. Working with bivariate data is substantially a matter of graphing and graph analysis. We are working with a very visual set of concepts here. The first step in comparing data is to set up a graph called a scatter plot, which marks each data point against those two variables. From here, we can start to make general conclusions about the nature of a relationship between these two variables, whether it's a strong relationship or a weak one, linear or curved, or follows some other tendency. Much of what we do at this point focuses on linear relationships, ones in which the variables change in conjunction with each other according to a basic slope-intercept formula. The tendency for the data points to congregate around a particular line is called correlation. Bivariate data with a strong correlation will show a pattern with a very narrow range. Given scales for each of the variables, we can actually quantify correlation, set up a number to show how close the data is to that particular line. The formula for setting up correlation is, to be polite, work-intensive. This is just one of those cases where running the numbers through the computer is not just thankfully easier, but much more effective overall. Once the computer has done its thing, or, God help you, once you finish dragging through all those calculations, you get a particular number r. R ranges from -1 to 1. A negative r in this case indicates an inverse relationship where one variable increases while the other decreases. An r of 0 means that there is no relationship between the two variables. Either the scatter plot is a total nebula, or one variable does not change at all compared to the other. Sometimes the data output will be r squared instead of just r. This value is used in certain specific calculations and situations, but for now we'll just consider r by itself. Once we calculate r, we can then decide whether there is enough of a correlation to suggest that there is some possible relationship between the two variables. We do this in conceptually just the same way that we have with everything else, with a comparison against the threshold value. If r is high enough, we can say that there is a correlation between the two variables. Assuming that someone is satisfied with the degree of correlation, we can then set up that line we mentioned earlier. This creation is called a regression line, a sort of prediction of how the two variables relate to each other. Again, the required work for setting up a regression line is a total headache, so let the computers do their thing, literally, which is why we call them computers. They compute. And we can see a line running through the data plot. This is our regression line, or line of least squares, the form of which is very similar to the classic y equals mx plus b slope-intercept form of a linear equation. Be advised that regression lines are super hypersensitive to outlier data points. Of course, this is merely data from a particular sample, and so in all likelihood we will have to consider how it relates to a population. And to do that, we of course create confidence intervals of sorts. Not so much around the regression line, but around a particular point on the regression line. Given a certain x sub 0, we can get a possible range around the y value. Yet again, the calculations are a complete beast. If spreadsheets need any justification to exist, bivariate data analysis would be quite sufficient. As a general takeaway though, collect the data, set up the scatter plot, find r or r squared, and then find the regression line. Those few numbers will tell you a significant amount about these possible relationships.